Hello, this is Gary Millette. This is ELE 110, Electronics for Technicians 1, the fall of 2022. And this is topic number 15, Diodes and Diode Applications. So let's get started. Turns out the first vacuum tube was a diode. There's a picture of some weird looking things on the right hand side. But what happened is they actually took the present day, back in the early 1900s, light bulbs and made modifications to them. So that's why they look like the way they do. So the first vacuum tube was invented by Fleming in 1904, over 100 years ago. This event was basically the start of the electronics era. This vacuum tube was essentially a evacuated light bulb with an additional metal element that could be connected to an external circuit. And again, there's a picture. If you go on the web and do a search, this is what you get. So we might want to talk about what the definition of electronics is. And a common definition of electronics is the idea or concept of devices that can control the flow of electrons. So even a switch would fall into that category. Basically a switch, human-operated device that either breaks or opens a circuit or connects or completes a circuit. So the vacuum tube, the diode vacuum tube, certainly is such a device. Current, or that is electrons, that form current, is only able to flow in one direction, from the cathode to the anode, in a vacuum tube diode. The name diode comes from the two elements, the anode and cathode, that comprise the device. So here's a diagram of the flow of current in a vacuum tube. So this shows a vacuum tube in this picture that has what they call a heated cathode, which gives off electrons. So the cathode basically is connected to the minus side of a battery, but there's also a filament that heats up the cathode, and the cathode could be a combination of the filament, itself. So you see electrons boil off. It turns out when there's a vacuum there in the glass enclosure, that electrons can kind of escape from the cathode, or the heater, whatever it's called. And if I put a metal plate inside the vacuum tube that's connected to the positive side of the battery, what happens, those electrons are attracted to it, and thus we have a current. So this is a diode vacuum tube conducting a current. But the current will only flow in one direction. So let's fast forward today to the present and discuss solid state devices. So here you see a colorful diode, and it's got p-type material on the left, kind of orangish color, n-type material on the right, which is kind of greenish color, and there's a purple in the middle called the depletion region. So the first device was a diode, semiconductor device. This two-terminal device only allows the flow of current in one direction. Now, the type of semiconductor material, either N or P-type, is determined by what's called the doping process, which we'll discuss a little more detail in the next slide. So you see this graphical representation of the PN junction here. Down below it in B is a schematic symbol which shows the anode is a triangle and the cathode is a straight line. And then you see another real component appearance that shows the diode looks kind of like a resistor, and it's got a stripe on it, and the stripe marks the cathode. So here's this slide that says of what the doping process is. The doping process adds either a column 3A, and column 3A materials make P-type, or column 5A. Column 5A materials make N-type material to the base semiconductor, usually silicon, and silicon's in column 4A. So here's a periodic table of elements, and chemists use this all the time to indicate the properties of elements and so forth. And you see the columns are labeled 1A, 2A, 3A, 4A. 4A are the carbon, silicon, germanium, and so forth. Tin is number 50, and lead is 82. We don't use lead or tin in semiconductors. We use the metalloids, which are silicon and germanium, 14 and 32 for their atomic numbers. And again, if I melt in some 3A materials, 3A materials will have fewer electrons and they form p-type material, or lack of electrons. If I melt into silicon 5A materials, and that would be like phosphorus and so forth, the ones in column 5A there, it turns out that they'll have an extra electron and they'll be, again, n-type silicon. And again, when we do this, when we dope silicon, pure silicon is very much an insulator. When we dope pure silicon with either 3A or 5A, we create semiconductors. So let's go back to this picture. This is a picture of a diode that's forward biased. It acts like a closed switch. So the diagram on the left-hand side shows a battery with a plus side attached to the P region and a minus side connected to the N region. And what happens is shows a PN junction, which is pretty thin, a very small depletion layer, and it shows electrons moving towards the N region and positive charge moving towards the P region. On the right-hand side is a schematic diagram. We have a resistor in there, R, which limits the flow of current so we don't burn the diode out. You see the symbol of the diode, plus on the triangle, makes it forward biased. Down below we show again the diode forward biased, plus on the triangle, minus on the line, and then we show a closed switch down below that. Here is the diode reverse biased, and it acts like an open switch. So now the diagram, you take a look and you see the PN junction, there's a much wider depletion layer. Minus is connected to the P-type, plus to the N-type. The diagram on the right-hand side, the schematic on the right-hand side, shows again plus to the line, and minus is closest to the triangle. Down below they show the biasing of the diode, and then down below they show an open switch. So the diode reverse bias acts like an open switch, or very little current will flow through the diode. So what are the applications of this device? Well, one of the first applications of diodes is to rectify AC power. We transmit AC around. There's a whole lore about the war between Edison and Tesla way back in the late 1800s about which way they wanted to take and transmit power. One was for AC and the other for DC. We won't go into it, but you can go to the History Channel. You go online to YouTube and look at these, what they used to call the Power Wars. And it turns out that they have a lot of programs that dramatize these power wars between, again, Edison and Tesla. So over the course of time, we transmit AC power around because it's the most efficient way to do it presently. And we can take and transform AC power to higher voltages to go to high tension wires where there's very low power loss as the power may be transmitted miles. And then when we get to a street level, what happens is we take and have a step-down transformer that brings it down to the 120 volts or 240 volts. Anyway, any electronics equipment needs DC to operate. So the diode only allows current to flow in one direction. So when AC, the flow of current in alternating directions, is applied to a diode, the output is DC, the flow of current in one direction. So there's a little schematic here. It shows the sinusoidal waveform supply on the right-hand side. It shows the plus half cycles and the minus half cycles. It shows a symbol for an AC supply or generator, and it shows a diode. And it turns out the diode has a resistor for a load. And what happens is the diode will act when it's forward biased as a closed switch, and then when it's reverse biased with negative input to the triangle, it turns out that it doesn't act like an open switch. Doesn't act like a closed switch, acts like an open switch. So what we get is a rectified output waveform on the right-hand side. Notice there's no negative half cycles. Now, I won't get into details, but that's called pulsating DC. DC, by definition, is direct current moves in one direction, and that's what it does. However, it turns out this pulsating waveform actually has an AC component in it, and again, we have to get rid of that somehow, so we actually use usually a filter, a capacitor, to get rid of the AC component of the DC, pulsating DC. So here's some typical diodes, rectifier diodes. There's a single rectifier diode on the left-hand side. Of course, it's blown up. Basically, the size of that thing is probably an 1/8 inch in diameter. On the right-hand side, we have a bridge rectifier, which has 4 of those diodes on the left-hand side, put into a single package on the right hand side. Notice that this bridge rectifier has a plus on it, a minus on it, and AC. So you apply AC from our prior diagram into the two middle terminals, and you discover that plus DC on the left hand side there and minus DC on the right hand side of that bridge rectifier. So a little more detail about power supplies. Rectification power supply block diagram is shown here. So the block diagram is on top. We have an AC input. Typically we have a transformer that adjusts the voltage level. Could make it higher, could make it lower. We do have some transformers with just isolation transformers, a 1-to-1 turns ratio, where we just want to isolate the input from the output. And we have the same turns ratio on the primary as the secondary. Then we go into a rectifier that converts AC to DC. That is either a half-wave diode rectifier, like we showed in one diagram, or the bridge rectifier that's shown here. Notice a bridge rectifier has positive pulses every, continuously coming out of it, whereas the half-wave rectifier only had positive pulse every other time. There's a filter. A filter is the capacitor you see in the schematic diagram. Removes voltage pulsations. So on the output of that filter you see a DC voltage with a ripple on it. Then we'll usually apply that to an electronic voltage regulator, which is an IC, and basically the output of that is just a nice DC voltage, steady DC voltage. So the schematic for this is shown down below here. Here's the bridge rectifier with D1, D2, D3, and D4. So the alternate pairs of diodes will conduct. On the output of that plus output to ground, we have a smoothing capacitor and then a load. So what happens is the resultant output waveform you can see is in the dotted line. The capacitor will charge up, and then in between pulses, the capacitor, since it has so much capacity, has charged up and it will start to discharge, but doesn't have enough time, charges up again, discharges a little bit, charges up again, and you get a fairly constant DC voltage coming out. So let's take a look at some other diodes. This diagram shows a typical LED. You notice that one lead of the LED is longer than the other. We apply plus to the longer lead, minus to the other lead, and what happens is the LED will light. So everyone's familiar with a common LED. This diode device emits light when forward biased. If I reverse bias, nothing happens. The color of the light depends upon the material used to construct the diode. We'll talk about that a little bit more. The symbol for it is shown down below, a diode with a couple arrows coming out indicating the emitted light. So if I wire this on a breadboard, here we have a 9-volt battery, which is enough to turn on an LED. Notice that the red positive goes to the top of the breadboard. The resistor comes down, and that is connected to the longer lead of the LED. The other lead of the LED goes to ground. The circuit here has a resistor in it. The resistor in the circuit limits the amount of current through the LED so it doesn't burn out. Typically that might be 180 to 300 ohms. We'd put that resistor. All depends on what the voltage is we apply. So this diagram showed to my 2-year-old granddaughter the other day, and I asked her what her favorite color was, and here you notice that we can produce just about every color of the rainbow. You see red, yellow, looks like 2 versions of green, then there's a blue one and a white one. The story about the white one is that actually inside there's about 3 LEDs, and it turns out they produce the primary colors, and when combined together that gives you white light, much like the light from the sun. All wavelengths combined into white. The blue LED was the last one to be perfected. Turned out there was a lot of materials processing science that had to go on before they could construct a blue LED, get the right materials that could be turned into a light emitting diode. So there's many other types of diodes here. This diagram shows the many other types. Many of these diode devices have different electrical characteristics due to different doping profiles created during manufacturing. By that we mean that maybe I have a diode where the N is N++, or heavily doped N, and the P side might be P-, or lightly doped P-type. So these different doping profiles created during manufacturing can give different electrical characteristics. And so these other diodes here have many different applications. And if I just read through, top left going down, signal diodes, Zener diodes. Zener diodes are quite common in power supplies as a voltage reference. Tunnel diodes can oscillate at very, very high frequencies. Gun diodes also are high frequency oscillators. You see light emitting diodes in the next column. A constant current diode, reactor diodes. Reactor diodes are reverse bias and act like capacitors. So if I have a smartphone or a FM radio, they're operated using reactor diodes to tune them. There's a crystal diode for detection of signals down the very bottom. The middle row shows infrared LEDs, Schottky diodes, pin diodes, avalanche diodes, again, all different types of diodes. If I go to the fourth column, I see photodiodes. There's a type of Schottky diode, it looks like, there in the middle, which might have been the other column. Step recovery diodes, vacuum diodes, laser diodes, silicon-controlled rectifiers. And the last column on the right, transient voltage suppression diodes, super barrier diode, point contact diode, and what's the last one? Peltier diode. I have no idea what that last one is, but I'll have to look it up. So again, all kinds of different diode types, basically different doping profiles. This is a review. We've already taken a look at this. I'll go back over it real fast. Here's an automotive application, a flyback diode. Flyback diode is used to protect active devices used as switches. When the relay activation voltage is removed, the magnetic field collapses suddenly, which induces a very high voltage. The diode, when the switch device is activated, is reverse bias, so it's not in the circuit like an open circuit. The magnetic field collapses and induces a voltage, which now will take a forward bias, that 1N 4004, and so there's a path for the current to go through as opposed to going through the switching transistor, which it might burn out. Here's another automotive application. You see the fuel pump relay. So again, there's a diode across that. That's a flyback diode again to take and not burn out the lead that comes from the blue wire there, which is from some type of switching transistor. We talked about this before. We call it solid state relays. Each one of these, we take and we apply a very small current on the left-hand side to switch a larger current on the right-hand side. And it's directly connected up in the top left, but in the top right you see a transistor there. The bottom left you see a logic gate with two inputs that both have to be high before that will, both have to be low in that case before that device will turn on the relay. Then there's a microprocessor there in the bottom right, where the pin number 5 would go low and turn on the infrared LED.